Well, I want to take a look at the volume of a solid. Now, I'm going to begin by approximating the volume of a solid by adding up the volumes of a bunch of approximating rectangular solids, boxes. Then I'm going to review a little bit from Calc 2, because I want to actually look at how we can do this in Calc 3 using an iterated double integral, and how we can evaluate that using Fabini's theorem. So that's the plan here. Now, first one I'm going to look at, jumping the gun you might say, is finding the volume of the solid pictured here, which is being modeled by z equals 0 on the bottom, z equals 9 minus s squared minus y squared, going to form the top, paraboloid for the top, and then and the sides are just the planes, x equals negative 2.5, x equals 2.5, y equals negative 0.5, y equals 1.5. These planes going up the sides, and we can iterate this thing with y going from negative 0.5 to 1.5, and x negative 2.5 to 2.5. Then iterate that with evaluating 9 minus s squared minus y squared, but z equals to the top. You're going to integrate that over that region, and you get 190 divided by 3. But how do we come up with that? How do we figure out that iterated double integral will give you the volume of the solid? Now you can approximate, as I said, using approximating rectangles. 10 of them gives you a 195 divided by 3, a little overestimate of the actual volume, which is 190 divided by 3 exactly. And what I can do, you can read the details if you like, I'm just going to do it here. Here's the solid. Now here's the solid with its top, and then its base down here, which is in this case nice simple base, a rectangle. And I divided the rectangle into 10 actually equal size sub-rectangles, and what I'm going to do here is I'm going to actually pick a point. You can pick the point in the middle, don't have to in the limit process, but I pick a point, in this case in the middle of each of those rectangles, use that point to evaluate the function that's giving us this top here at that point, which will give us a z value right here on the surface. That would be the height of what I'm going to use for an approximating rectangle. So here's a few different sort of points of view of this. There's the solid again. And so here I'm drawing in these approximating rectangles. You wouldn't want to see me draw in more than 10. It would take much too long. But I can give you a sense of what's going to happen in the limit processing and the finite approximation process. So a finite approximation to the volume of the solid will consist of computing the volume, which we can certainly do, of each one of these approximating rectangles. Got 10 of them. You can notice that it doesn't give a real accurate picture, just 10 boxes. It actually gave you 65 for the volume instead of 63 1/3. If I had constructed 40 boxes, I've gotten 63.75. I actually did that and computed the volume of each of them using Maple, the computer algebra system. Just wrote a little program to do it. And then using that same program for 160 boxes, I got that, 640 boxes, 2,560 boxes, 63.3398. That's getting close. You're off by not too much. I mean, if you truncated this thing right here, you have 63.33, and you'd be pretty accurate. The 9, we're off by a bit. I could have taken that up to many thousands of boxes, and Maple would have computed it for me. I didn't go any farther than this. Now, what we want to do here is compute the exact volume, which you can see me doing here, and justify it. I'm trying to teach something here. So the idea is the exact volume will be the limit as the number of approximating rectangles approaches infinity, with the stipulation, I'm pointing at you up here with my cursor, the norm of the partition approaches 0, which means when you partition into rectangles and you take the limit as the number of partitioning rectangles approaches infinity, you've got to do it in such a way that you don't have one of them staying stagnant. You know, you can't have one of these rectangles remain with positive dimensions. Even if all the rest of them, the numbers approaching infinity, you got to have every one of them having a base approaching 0 by 0. So in this limit process, what this little symbol here is telling you is you're taking a limit as n approaches infinity of this sum, with the function evaluated at some point in the ith rectangle gives you the height of the approximating box, and delta h sub I is giving you the area at the base of the ith box, so that's giving you the volume of the ith approximating box. But you got to make sure in computing this limit as n approaches infinity that each side of your approximating your box down here is approaching 0. Now, the definition of a double integral is this limit. Well, the double integral over a region. So I had a rectangular region I just showed. Here we're looking at a region that wouldn't be rectangular. One side is maybe it's a portion of a parabola in the picture. But this double integral notation equals this limit if the limit exists. If the limit exists, we say this is integrable, but how do we actually integrate it as you're used to thinking of integrating by finding antiderivatives of functions and computing the thing exactly? It may help to see how this is going to be pulled off by taking a little review of something from Calc 2, volume using a cross-section area function. Now, in Calc 2, we study how to find the volume of a solid whose cross-sections are identifiable as maybe a circle or a ellipse, or in this picture, an equilateral triangle. What we're looking at here is going to describe a solid whose base is bounded by y equals x squared and y equals x plus 2. It's lying in a parabola intersecting here at -1, 1 and here at 2, 4. And then the cross sections of the solid being modeled here are equilateral triangles. I've pictured 2 of them here. Actually, I pictured 2 sides of them. The third would be from here to here. This is from the point on the line to the corresponding point down there on the parabola. It would actually give you a cross section. And if the cross sections are equilateral triangles, and add distance from here to here, the same distance from here up to here and there up to there in this cross section, if the cross sections are equilateral triangles. So here's a picture of what the solid looks like, and you can actually play this thing here, and you can look at the cross sections being pictured. These cross sections are equilateral triangles, and you can see as we move across the base of the solid that the cross sections are equilateral triangles. And so there I have. I'm coming back again, but so let's go on. So the solution would look like this. Your area of an equilateral triangle is a side squared times square root of 3 divided by 4. So the cross-sectional area function would be a side, which is the distance from the line on top to the parabola on the bottom, squared times square root of 3 divided by 4. So the volume then, you go from A to B of the cross-sectional area function. X went from -1 to 2, showing x integration from -1 to 2 of our cross-sectional area function gives you 81 times square root of 3 divided by 40. That would be the exact volume of that solid. But the hang-up here is the cross-section had to be identifiable as like a rectangle, a circle, equilateral triangle like I use here to form that cross-sectional area function, at least in single variable calculus, like calculus 2. So there's a little summary of what I just reviewed from calculus 2. Well, here's the thing. Could we do it if the cross-sections weren't nice like equilateral triangles? Now what I want to do here is another Calc 2 problem, but use it to build a way to do this in Calc 3 using an iterated double integral. So I'm going to again find the volume of a region formed by, in this case, revolving the graph of y equals 4 minus x squared, this little parabola here, for x between negative 2 and 2, about the y-axis. You can actually just take half of that, revolve this about your y-axis. You're going to form a solid revolution, and you could actually find the volume of that, still using Calc 2, review from Calc 2, using the disk method, or the cross-sectional area function method. Your cross-section here going to be circles, and the cross-sectional area will be pi times the radius squared. And the radius of that circular cross-section will actually be a distance from here to here. So it will be like the x value there. So you take this equation of the parabola and solve for x. The parabola on one side, portion of it would be x equals the positive square root of 4 minus y, for y between 0 and 4, y going from 0 to 4. So this method will give you the volume of that solid revolution by integrating from 0 to 4 pi times your cross-sectional radius function here squared. Just give you 4 minus y. Pretty simple integration. I even put in all the steps here. You get 8 pi for the volume of that solid revolution. That would be the easy way to find the volume of this particular solid. What I want to show you is a hard way to find the volume that shows you how you can find all kinds of volumes using an iterated double integral. So what I'm going to do is find the volume of the same solid, but in this case, for my cross-sections, I'm not going to go in the direction that makes the cross-sections circles, but in the direction that makes the cross-sections portions of a parabola. They are not going to have a nice immediate area function for. You actually can derive an area function for that, but I'm not going to take that way out. I want to build something else. If you wanted to pause this, I could actually go. I got this on YouTube. You go into YouTube here, and you can actually pause it any place you want. Just keep clicking in here. You can see different cross sections, which are going to be like there's one cross section. Maybe a portion of a parabola. So back to my animation here. So what I'm going to do, well, actually, let's take another still look at it. Here we're looking at, here's the solid revolution, or the surface of revolution here. I hollowed out the bottom, left it hollow, and got these planes intersecting it in portion of parabola. So this area, this like a portion of that parabola right there, is what I want to compute as my cross-sectional area function. Now, what I'm going to do to do that is this. We want to look at the cross-sections as parabolas with z equal to a being the plane intersecting my parabola here in these parabolic cross-sections. And for z equal to some number a, the actual area would be the area of this thing pictured here. That would be the area of the cross-section, with x going from negative square root of 4 minus a squared to positive square root of 4 minus a squared, y going from 0 4 up here, I guess. Well, not always getting to 4, actually. Here I got whatever 4 minus x squared minus a squared, so the y value up here is going to be not 4 in this picture, but we're having 4 minus a squared. Anyway, the area of this portion of a parabola would be the integral from this value of x to that one of y equals 4 minus x squared minus a squared. That would be the area of one of these cross sections. Now, as a function of z, you see, I can come up with a cross-sectional area function as a function of z. Just replace the a with z, and whatever value of z you add along here, the cross-sectional area will be this integral right here. So the volume of our portion of a paraboloid would be the integral from -2 to 2 of the cross-sectional area function, in this case as a function of z, which was that function right there, function of z. And we've got an iterated double integral, which does evaluate to 8 pi. I'm not going to grind it out. I actually admit I computed that on Maple, but it does give you the correct 8 pi, which is the volume, using the disk method, of that solid. So what we're looking at here is a double integral defined as an integral over some region, in this case of the a coordinate plane, xz coordinate plane in this case. dA can be iterated as an integral where the z goes from a to b, in this case -2 to 2, and x goes from some function of z to another function of z, and you can see what that was here, of the function of, in this case, x and z that we're integrating. Pretty cool, I think. So, brings us to a theorem for evaluating double integrals. Theorem is going to be stated for z a function of x and y, but you can do it as I just did for y a function of x and z, or x a function of y and z. And that's what I just presented. It's called Theorem 14.2. This is from the Lawson Edwards calculus textbook, called Fabini's theorem. And theorem says if f's continuous on a plane region R, and R can be iterated, you can actually compute the double integral with this iteration. This one's y and z, here is x and y, and this, again, in both cases you're looking at z a function of x and y, but you have variations as x a function of y and z, and y a function of x and z. All kinds of possibilities now for computing volumes using an iterated double integral, if you can come up with this this function right here. In effect, if you come up with your cross-sectional area function as a iterated single integral, you can then construct your iterated double integral and calculate your volume. For example, if we wanted to find the volume of a solid or a region of space, pictured here with this base, bounded by the plane z equals 0 on the bottom, by the elliptic paraboloid z equals 4 plus x squared plus 2y squared on the top, and then on the side, along is the plane. Now remember, y equals x plus 2 in the xy coordinate plane is a line, but in space with the z-axis is a plane. This plane pictured right here. Then cylinder y equals x squared minus 4. A cylinder in space is, you can get a right cylinder if you got a curve y equals a function of x in this case, involving only x and y, which this would be a parabola, in the xy coordinate plane. In space, it'd be called a cylinder. Just take that parabola and draw all the lines through the parabola perpendicular to the xy coordinate plane, going in the z direction. You get the surface in space. You can see a little big of it here. One side of this solid is this cylinder. The other side is this plane, and the plane is equal to 0 on the bottom, and this elliptic parabola is the top. So to compute the volume, we can actually model it as an iterated double integral, iterating over this region pictured right here. That's the base of the solid, where you can see x going from -2 to 3, and y going from the parabola up to the line. So if we iterate that, doing a dy dx iteration, we got y going from the parabola up to the line, and x going from -2 to 3, and then an argument for our integral would be this paraboloid. You can generalize that a bit, because if the bottom hadn't been z equal to 0, but z equal to -2, you actually have this minus the -2, or that plus 2. That would work. Now, of course, that could reconstitute some of this other stuff, but you literally, the argument in here can be one function of x and y minus another function of x and y. It could actually give you, the bottom to the top. So it's really a powerful tool. We're just scratching the surface here, but this volume can be computed. You grind that out. It comes out to 23,375 divided by 84, a little over 278. Really cool that we can compute these volumes. So there was the base, a little bigger picture of it. Again, you're going x -2 to 3, and then y going from the parabola up to the line, and a little picture of your solid here with that the one playing on the side, playing on the bottom. I kind of wish I had gone live in Maple and could flip this thing around for you to see it, but I didn't. So I guess we'll just call it a video. Pretty cool. Stay safe.